So the substitution rule, or our U substitution, this is the reverse process of using the chain rule. So let me remind you what the chain rule was. The chain rule said if we took the derivative of a composition of functions, so f of g of x, our derivative was the derivative of the outside evaluated at the inside times the derivative of the inside. And we worked with this a bunch this semester, so this should be nothing new, right? The derivative of the outside evaluated the inside times the derivative of the inside. So what we want to do is reverse this process inside an integral. So what you can picture is we'll be going in this direction. So what we need inside an integral, if we have the right side, which is f prime of g of x times g of x, then going in the opposite direction, we would end up with f of g of x. Okay, so all I did, you can see my red arrow, all I did was go in the reverse direction, right? If what's inside the integral matches what's on the right side there, then we end up with f of g of x. Oh, I forgot. Plus c, f of g of x plus c, right? Our constant of integration, that's really important. So the challenge is, in most cases, the integral isn't going to be set up perfectly for us. We're not going to see exactly that f prime of g of x times g of x. Oh, what did I miss? I messed something up here, right? The derivative of the inside. Sorry about that. The derivative of the outside evaluated the inside times the derivative of the inside. Sorry, I dropped a prime there. Okay, so the challenge is that sometimes we might not see that f prime of g of x times g prime of x exactly. And so sometimes we might have to algebraically manipulate what's inside the integral to get that exact expression so that we can apply this chain rule in reverse. So first I'll show you a really easy example of something that works out perfectly. So for example, if we have cosine of x cubed times 3x squared dx. This works out perfectly that the derivative of sine of x cubed, we know the derivative of sine of x cubed is the derivative of the outside evaluated at the inside times the derivative of the inside. So because we can see that match up exactly right, we know that this integral is going to be equal to sine of x cubed plus c. So here's one that works out exactly perfectly. But in most cases, we're going to have to do a little bit of work first. So I told you this was called U substitution. So let's take a look at this exact same problem, this cosine of x, integral of cosine of x cubed times 3x squared dx. And we'll do this using U substitution so I can show you what that looks like. So U substitution. The idea is to use a new variable, u, to represent g of x. G of x is our inside function, right, in this chain rule notation. And then rewrite the entire integral in terms of u. So let's go back to my first example. Let's go back to the integral of cosine of x cubed times 3x squared dx. Okay. The way we approach this with u substitution is we always let u be g of x. And remember, g of x is our inside function, what's inside that composition. So here we see this x cubed is inside cosine. Okay, so that's how we decide what u is going to be. So we let u be x cubed. Okay, then what we do is we find du dx. The derivative of u with respect to x is 3x squared. Now, the next thing we do is using something called differentials. What we can do is separate that du dx. Okay, so I'm going to separate this du dx, and I'm moving the dx to the other side of the equation. So I'm writing this as du is equal to 3x squared dx. So what you want to think about this is we're not actually like multiplying both sides by dx, but when we split this up, we call these differentials, and so we can actually split that up and move that dx over, and I'll show you how this works out. So the next thing we do is we go back to this integral we had, and we want to write everything in terms of u. So the first thing we have is that x cubed is u, so I have cosine of u. Now, if we look at this next part, here this 3x squared dx, that perfectly matches what we have over here. Okay, so 3x squared dx is just equal to du. Now that we've done u substitution here, we can easily compute the antiderivative, the integral, the indefinite integral, right? The antiderivative of cosine of u, we know is sine of u plus c. Now our last step is always to plug u back in. And so we get sine of x cubed plus c, which is what we got when I did this the first time around. Okay, so this is what u substitution looks like. And I'll do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got like 10 examples of u substitution for you today. Any questions so far? And on your homework, I'm going to ask you in the chat box, actually. We've got 9 people here today. So I'm going to ask you in the chat box today for each of these problems, what you think you should let u be. And remember, u should be the inside function, the function that's inside the composition. On your homework and on your quiz and on your final exam, some of the problems don't tell you what u should be. And some of the problems would say, like this one says, make the substitution u is equal to x cubed. So some of the problems tell you what u should be, but in general, as you're moving on to physics, engineering, higher calculus classes, you're going to have to figure out what u is yourself. So in the chat box, every problem, I think I got 10. I want you guys to let me know what you think we should let u be. So first one, the integral of tangent to the 4th of x times secant squared of x dx. I'm going to give you a little hint here. Where we see this tangent to the 4th, I'm going to rewrite this as tangent of x to the 4th times secant squared of x dx. Okay, so in the chat box, what I want you guys to do is tell me, what do you think we should let u be? What is the function that's inside our composition? Yeah, the tangents. Okay, so This is my inside function. And you only really have two options, right? Either tangent or secant. If you had rewritten that secant squared as secant of x all squared, you only had two options. And so the good news about the u substitution process is if you pick the wrong thing to be your inside function to let be u, pretty quickly you're going to get to a point in the problem where you're stuck. And that should just remind you, like, go back and the other thing should be u. So in general, it's going to be whatever is the inside function. So we're going to let u be tangent of x. Then what we do is we write out du dx, the derivative of u with respect to x. And we know that the derivative of tangent is secant squared. So our goal is to also have that secant squared of x in our integral, which we do. So we're setting this up just perfectly. The next thing we do is we separate these differentials, and I write this as du is equal to secant squared of x dx. Okay, so now what I'm going to do is rewrite my indefinite integral. Tangent of x, we let that be u, so I have u to the fourth. And then check this out, the secant squared of x dx, that's exactly equal to du. So now using the reverse power rule, we have that the integral is u to the fifth over 5 plus c. The last step is we have to put u back in. So u was tangent of x. So I'm going to write my final answer as 1/5. And then we have tangent to the fifth plus c. Now what you can always do is you can always check your answer, right, by taking the derivative of this. And you should get your integrand, what's inside your original integral. So you can picture 1/5 tangent fifth, right? We take the derivative of the outside, so the 5 would come down, 5 and 1/5 cancel. We decrease our power by 1, so that would be tangent to the fourth times the derivative of the inside, which is secant squared. Okay, so you can always do this in reverse. Take the derivative of your final answer and make sure you get the integrand. Any questions on this? We'll do plenty more. Any questions? Shout out to my high school teacher. So how did we get u to the fifth? So from this step, in order to find the antiderivative, we use the reverse power rule. So we're doing the opposite of the derivative. So the reverse power rule says we add 1 to our exponent. So that's u to the fifth. And then we divide by that new exponent. So reverse power rule says the integral of x to the n is x to the n plus 1 over n plus 1 plus c. Right, and that's the opposite of just the regular power rule, which said that the derivative of x to the n is n times x to the n minus 1. We're doing the opposite. All right, any other questions? So I have these weird memories of high school. And I don't know if you guys had some weird things that always stick out to you as well, but I graduated from high school in 1999. So there's these funny things that always stick out. So I can remember when I was in high school calculus, my calculus teacher was Mr. Miller, and obviously he had a big impact on my life as I decided to be a math major. But I distinctly remember doing U substitution in 1999. And every single time we're doing U substitution and Mr. Miller would ask the class, what should we let U be? All of us all at once said, let U be 40. Because there's this band called UB40. They sing like Red, Red Wine and some other good classics, but every single time. And it was like brutal. It was like for a month straight, we're doing U substitution. Let U be 40 every single time. So funny things you remember. All right, any other questions before we move on to the next example? All right, what's their other popular song? I Can't Help Falling in Love with You. That was their big one. Now I'm really dating myself now that I told you guys when I graduated high school. All right, next one. the integral of 4x times the square root of 1 plus 2x squared dx. Okay, so in the chat box, more than one person this time. Let's try and get 5 of you answering. In the chat box, tell me, what should we let u be? Not 40. What should we really let u be? What you want to be on the lookout for is u should be your inside function. What's inside the composition. So go ahead and use whatever shortcut notation you want. Tell me what we should let u be. Perfect. Okay, so here we see that this 1 plus 2x squared is inside our square root. Okay, so the function that's inside, that's what we let u be. Okay, so what was I going to say? And again, this is very forgiving. If you accidentally do the other one, you'll get stuck really quickly. And then our goal is to see the derivative of the inside somewhere else in our integral, which quickly we can just eyeball that the derivative of 1 plus 2x squared is 4x. So we see that derivative outside. So that works out perfectly. Okay, so let's go ahead and proceed. I'm going to let u be 1 plus 2x squared. Then the next thing we need is the derivative of u, which is 4x. We split these differentials and I write this as du is equal to 4x dx. Okay, so we are also looking for this 4x dx, and it is okay that this 4x dx is in 2 separate places. That's totally fine. Remember, whenever we have multiplication, right, it's 4x times the square root of 1 plus 2x squared. Multiplication is commutative, which means I could actually just move that 4x around if I wanted to. So it's okay that those two things are split up like that. Our next step is to go ahead and rewrite this integral in terms of u. So I have the square root of 1 plus 2x squared, we let that be u. And then 4x dx is du. Before I apply our reverse power rule, I think it's always helpful to write this square root as the 1/2 power. Okay, so my recommendation for you on all of these problems, and as it has been all semester, is whenever we have a radical expression or an exponent in our denominator, is to make sure we rewrite that so we can easily apply our power rules. So our reverse power rule says that that integral is equal to, we add 1 to our power, so 1/2 plus 1 is 3/2, and we divide by our new exponent, and then we should never forget our constant of integration plus c. The last thing we should do is plug u back in. So I'm going to write this a little bit nicer. So divided by 3/2 is the same thing as multiply by 2/3. And then we have u to the 3/2. So u was 1 plus 2x squared. And then we have plus c. Now remember, if you want to check this, you can always take your derivative of your answer and you should get the integrand. So you can picture when we take the derivative, right, we apply the power rule. You guys are backwards from me. I keep doing this the wrong way. We would take that 3/2 and bring it down in front. The 3/2 times the 2/3, both cancel each other out. So we'd get 1 plus 2x squared to the 1/2 times the derivative of the inside, which would be that 4x. Okay, so that works out perfectly. So in general, what you want to be on the lookout for when you're computing integrals is whenever we have that expression inside a square root, inside a trig function, inside whatever, that is something other than plain old x, we need to do this reverse chain rule, which is called u substitution. Any questions on this? Okay, let's do some more. So next one, I have the integral of sine of x to the 4th plus 5 times x cubed dx. Okay, so again, in the chat box, I'll have you guys help me with all of these problems. Let's get at least 4 or 5 people telling me, what should I let u be? Great. Okay, so in general, we always let u be our inside function. Okay, right? In terms of f of g of x, that composition, u was g of x, or inside. So I'm going to let u be x to the fourth plus 5. The next step is to take the derivative. So du dx is equal to 4x cubed. The next step is we split those differentials, and I write this as du is equal to 4x cubed dx. Now, this one is a little bit different than our previous problems. Let's take a look at what we have inside our integral. What we have inside our integral is not 4x cubed dx. It is just x cubed dx. So what I want to solve for what we do have inside our integral. So my next step here is to divide both sides by 4. And we have that 1/4 du is equal to x cubed dx. And this x cubed dx, that is what appears in our integral. So where I see that x cubed dx, I'm going to sub in 1/4 du. So the idea is we want to match what's inside our integral with what's in this equation. Okay, so here's how it looks. We have the integral of sine x to the fourth plus 5, that is u. And now x cubed dx, we just figured out that's not equal to du, it's equal to 1/4 du. Our next step is applying our rules of integration. We know that we can pull this constant out in front, right? Our constant multiple rule. So now I have 1/4 times the integral of sine of u du. Now we know how to compute this integral very quickly. So we know that the integral of sine of u, that the antiderivative is negative cosine of u plus c. Our last step is to put u back in, and then I will simplify this 1/4 times the negative. I'm going to write it as negative 1/4 times cosine of u, which is x to the fourth plus 5 plus c. Now, again, I would suggest once you find your answer, especially for the final, you can take the derivative of your answer and you should get the original integrand. Integrand meaning what's inside the integral. I want to show you a different way of doing this problem. So let me put a big fat or here and let everybody get caught up and show you the method that u substitution we can do kind of like a quick little shortcut that I like shortcuts. If you always want to go through this long process, that's fine too. Any questions so far before I show you the second method? Okay, so the way that I would conceptualize this is that what we know is in order to be able to make this u substitution work, we need to see in our integral, in that integrand inside the integral, we need to see the derivative of the inside, right? The inside being x to the fourth plus 5th in this original problem. So here's how I would do this in my head and what clicks with me a little bit better. So we already identified right off the bat that this is the inside function. So what I know is that in order for this reverse chain rule to work, I need to have the derivative of the inside. So the derivative of the inside is 4x cubed. Well, looking at this integral, I only have x cubed. So in my head, what I would do is tell myself I need a 4 here. Now I can't just randomly multiply by 4, right? Because that changes it. So if I multiply by 4, I also need to divide by 4. And if I multiply and divide by 4, that's multiplying by 1, which doesn't change our expression. So in my mind, what I would do quickly is recognize I need a 4. So in order to make this a net 0 change, I also need to multiply by 1/4. Now you can see quickly, like, I can do this in my head because I see that the derivative appears right here. I would have 1/4 negative cosine of x to the fourth plus 5 plus c. Okay, so If you want to do it this method, you're certainly welcome to do so. I'll go through the formal u substitutions for all of the problems. Actually, I'll show you the other way a couple more times for those of you who like shortcuts. If you hate shortcuts and you like the formal process every way, by all means, please go through that formal u substitution, but there's a way to do it a little bit quicker. Any questions on that? I got 7 more for you. And in general, in real world problems, when you see these problems come up in physics and engineering and whatever else, your integral isn't going to be perfectly set up with a chain rule. So you're usually going to have to do this u substitution. And then even further, in your next calculus class, you're going to do something called integration by parts, and you'll learn how to compute integrals of things with products in there, so which we won't do in our class. So there's all sorts of other methods of integration that you have coming your way. So first up in the chat box, tell me, what should I let u be? I can't even say that without thinking UB40. That'll be stuck in my brain forever. Right, 3x. Okay. So we let u be 3x. That means that du dx is equal to 3. Splitting that, we get du is equal to 3 dx. Okay, so doing this u substitution, what we want to solve for is what we see in that original integrand. So I'll divide both sides by 3, and I have that 1/3 du is equal to dx. So now rewriting this, I have the integral of cosine of u, and then dx is equal to 1/3 du. The next step would be to move the 1/3 out in front. Now we can compute this integral pretty quickly. We know that the antiderivative of cosine is sine. Our last step is to put u back in. And then if you want to check, you can check that the derivative of our answer is the original integrand. Let me put a big fat or. I want to show you using the shortcut, but I need to go blow my nose, so I'll be right back. They just announced yesterday in the news, I just read it, that this fire that's raging in California, the Dixie Fire, is now the largest fire in California history ever. So it's very sad, but the smoke here, I'm sure you guys are feeling it too. It's just wreaking havoc on my sinuses. So sorry for blowing my nose during class all the time this term, but smoke is crazy. Are there any questions on this problem? I'll show you the second method as well. Okay, so the way that I like to do this in my head, if you like shortcuts, let's start back. Oops, what did I push? Let's start back with our original integral. Okay, so the way that my brain would work is that I know if we're going to apply the reverse chain rule, the inside is going to be 3x, and then I need to see the derivative of that inside my integral. So the derivative of 3x is 3. So what I need is a 3 in here, which means I have to do a 1/3 on the outside. 1/3 times 3 is 1. I can't change this, right? I can't just randomly multiply by 3. I also have to multiply by 1/3 so that we're not changing it. Okay, so that's how I would view it. And then in my mind, right, we would get 1/3. The antiderivative of cosine is sine of 3x plus c. Again, this is just a shortcut you're welcome to use. This is how my brain sort of processes it. If you want to go through the formal u substitution every single time, that way always works. This is kind of like as you get in higher calculus classes, if you have to do this frequently, maybe this is helpful. Any questions on this? Okay, let's do some more. How about, this one's a little bit tougher. The integral of secant squared of x over 3 times tangent of x minus 1. Okay, so think about this one for a second. And we need to identify what's the inside function. What should we let u be? Now, the giveaway is that once we figure out what u is, we also need to see the derivative of u in our integrand. I forgot my dx here, sorry. We also need to see the derivative of u. Okay, so you kind of have two options, right? Either secant squared of x or 3 tangent x minus 1. So think about that for a second, and then tell me what you think I should let u be. Okay, so once you've thought about what u should be, ask yourself what's the derivative of that? And do you see that easily in our integral? That's the dead giveaway. Right, you kind of only have a couple of guesses. Okay, so this one's tricky. In general, when we have things that are set up like this in rational form, in general, whatever the denominator is, we're going to let u be that. So what you can picture is, I keep saying like the function is stuck inside, right? Stuck inside sine, stuck inside cosine, stuck inside the square root. You can picture that this 3 over tangent x minus 1, that's like stuck inside our reciprocal function. So the reason why this works out is if we let u be 3 tangent of x minus 1, the derivative of that is 3 secant squared of x. And remember, our goal is to see that derivative inside our integral as well. Okay. If you did this the opposite way and you let u be secant squared, the question would be, what's the derivative of secant squared? I have to look at my note sheet because I can't even tell you what the derivative of secant is off the top of my head. The derivative of secant squared would be 2 secant of x times secant of x tangent of x. That's really messy, and we certainly don't see that in our integral. Okay, so that's kind of the way you would figure this out. But it could also be guess and check. So if you're doing this in another class and you're not sure what to let u be, try it out. So if we let u be secant squared of x, then du dx would be 2 secant of x times the derivative of the inside, which is, what did I say, secant tangent, which we definitely don't see that anywhere in our integrand. Okay, so that'll tell you we didn't do the right thing. Any questions so far? Okay, so now in our integral, we see secant squared of x dx. So I'm solving for this secant squared of x dx. So first I'll split this, right? Oops, how do I got the pencil? It's funny, I feel like I hear myself saying oops so much when I'm teaching with this iPad. It's funny to watch recordings of yourself too. I notice I say okay a lot. Okay, and oops. So first of all, I'll split this du dx up. And then I want to solve for what we see in the integral, which is, oh, I should get rid of this. We want to see what we see in the integral, right? That's secant squared x dx. So I'll multiply both sides by 1/3. Now we're ready to rock. So in the numerator, secant squared x dx, that is equal to 1/3 du. So what I'm going to do is, we know that's equal to 1/3 du. I'm going to go ahead and move that 1/3 outside of our integral. So I end up with 1 over 3 times tangent of x minus 1. We let that be u. So our next step is to take the antiderivative of 1 over u, which we know the antiderivative of 1 over u is ln of the absolute value of u. Don't forget these absolute values. That's really, really important when we're finding antiderivatives. Our next step is to plug u back in. So we have 1/3 times ln of the absolute value of 3 tangent of x minus 1 plus c. Now remember, if you want to check, you can take the derivative of your final answer and you should get the original integrand. Now the way that one works out with the absolute value signs is a little bit trickier, but what you should pay attention to, like when you're checking on homework or on the quiz or on the exam, is you can check this without the absolute values because going in the reverse order, those don't really track. But if you just had 3 tangent of x minus 1, right, the derivative of natural log of something, we put that something in the denominator and its derivative in the numerator. All right, any questions on that one? Okay, let's do a few more. How about the antiderivative of e to the negative x dx? So in the chat box, tell me, what should I let u be? Yep, negative x, good. So whatever's stuck inside, so that negative x, that's kind of stuck inside that exponent there. So let u be negative x. So du dx is equal to -1. So du is equal to -1 dx. And our goal here is to solve for what we have in the integral, which is only a dx. And so I multiply or divide both sides by -1. So I get -1 du is equal to dx. So dx is equal to -1 du. I'll go ahead and just move that -1 out to the front of our integral. We know that the integral of e to the u is just e to the u. Our last step is to put u back in, which was negative x. And that's it. And again, you can check this by taking the derivative and you should get the original integrand. You're also welcome to do this. I won't do this for all these problems. If you want to do this using the shortcut method, what I would notice is I need to have a -1 dx. So if I multiply a -1 out here, I also have to multiply a -1 out there. Any questions on this one? Okay, next one. How about the integral of x over the square root of 1 minus 9x squared dx? Okay, so the first thing we should do is identify what we should let u be. And in general, it's what's inside, stuck inside. So here's u. Our process is next up, we find du dx, which is -18x. We split up that du dx, so du is equal to -18x dx. We want to match with what we have in this integral. So in our integral, we only have x dx. So my next step is to move that -18 to the other side. So I have 1 over the square root of u, and then x dx is equal to -1 over 18 du. So I'll bring that -1/18 outside my integral. And then as we've talked about already, usually when you have radical expressions or any exponents in the denominators, I think it's easier to apply the power rule once we rewrite this. So I'm going to write this as u to the -1/2. Our reverse power rule says to find the antiderivative, I add 1 to the exponent and I divide by my new exponent. So -1/18. And then I also have 1/2 in the denominator. Remember, that's we multiply by the reciprocal, so I multiply by 2. So those combine to -1/9. I'll put my u back in, which was 1 minus 9x squared. And then we have to the 1/2 plus c. And as a reminder, you can take the derivative of this and make sure that you get the original integrand. Give you guys a few seconds to get caught up here, and then I just have 3 more examples for you. And they're all sort of the same type of problem. Any questions on this one? Okay, let's do 3 more. How about the integral of the cube root of ln of x over x dx? The first thing we always want to do with u substitution is identify what we should let u be. And visually, the way we do that is we look for the inside function. So what do you guys think? What should I let u be in this example? What's stuck inside something else? Yeah, the ln of x. Now, the idea is we want to be able to find the derivative of u in our function as well. So think about this, the derivative of ln of x. Someone tell me in the chat box, what's the derivative of ln of x? 1 over x, okay? So we do see that. Here's our 1 over x dx. Okay, so if you want, if it helps you visualize this, we could write this as cube root of ln of x times 1 over x dx. Okay, so we're going to let u be ln of x, then du dx is equal to 1 over x. Moving our dx over, we get du is equal to 1 over x dx, which we see right in our integral. Okay, so remember, I think that anytime we have a radical expression like this, it's easier to write it as an exponent so we can quickly apply our reverse power rule. So we have u, and cube root is the 1/3 power. And then that 1x dx, that is du. Now that we've done this u substitution, doing the reverse power rule is really easy. Our reverse power rule says we add 1 to the exponent, so 1/3 plus 1 is 4/3, and we divide by our new exponent, and then plus c. Our last step is to put u back in, so I have ln of x to the 4/3 over 4/3 plus c. We don't have to simplify this, but usually if we have a fraction in our denominator, we would write it like this instead. WebAssign should accept either form. Any questions on this one? All right, my second to last example. This one you guys really have to think about. So let me put it up, and then I'm going to pause I'll pause for a few seconds and I want you guys to think about how you would approach this last one. You do really have to think about it. How about the integral of tangent of x dx? Any ideas on how I should start? Your hint is eventually we will need to use U substitution. Okay, so if you had me for Math 127, I told you the two most used Math 127, which is trig, the two most used trig formulas. Just backing up a second. In general, where sine squared of x plus cosine squared of x is equal to 1. That's called the Pythagorean identity. The second one is called the quotient identity. I was going to write reciprocal. That's not right. Quotient identity. These are the two most used, I think. So somebody tell me, tangent of x, I can rewrite it as what quotient? What over what? Sine over cosine. Okay. So now let's go back to our integral. Now if I rewrite this as sine of x over cosine of x, now we can apply U substitution. So the question is, what should we let U be? In general, when we have it written in this fraction form, in general, what we're going to let U be, as we did, in the previous problem, is we'll let what's in the denominator be U. In general, it'll work out. And remember, we only have two options here. So if we start with let U be sine, and we try and work it out, it doesn't work out very easily, that just goes and clues you in that we need to switch what we let U be. So let's let U be cosine of x, then du dx is equal to, the derivative of cosine is negative sine. So moving our dx over, I get du is equal to negative sine of x dx. What we want to do is match up what's in our integral here, and we almost have that. So I'm going to multiply or divide both sides by -1. So now inside our integral, we have 1 over u. And then that sine of x dx is equal to negative du. I'm going to go ahead and just move my negative onto the front of the integral. So now we know that the antiderivative of 1 over u is ln of the absolute value of u plus c. Last step, we put u back in. And there we go. Now this one's tricky, right? We went through the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of tangent is secant squared. But when we went in the opposite direction, right, trying to find the antiderivatives, we did not evaluate the antiderivative of tangent. Turns out that the antiderivative of tangent of x is negative ln of the absolute value of cosine of x plus c. Okay, so that one's a little bit, I would say, not obvious. Any questions on this? Okay, I have one more example for you today. And in all of these examples and in your homework for this section, you'll be doing this U substitution with indefinite integrals, meaning we don't have limits of integration. So what I want to show you this last problem, I'll put a big line here. If you want to write this down, cool. If not, it doesn't apply to our class. But I want you to see this because it applies to your other classes. Like maybe you'll see this in physics or something. So let's say we were doing the integral from -1 to 0 of x squared times x cubed plus 1 to the 4th dx. Now, the first thing we notice is what's inside here should be u. So our clue is to do u substitution. Now, the catch here, and again, this doesn't apply to our class. So if this is your last math class ever, you can zone out from my last example, but I want to show you how this u substitution works. The catch is these values, these are x values. So technically, when we do u substitution and rewrite the integrand, the part inside the integral in terms of u, we cannot write from -1 to 0 because those are x values and those variables don't match up. So usually what we do is we take a step back and first we just work on the indefinite integral. And if I let u be x cubed plus 1, I need a 3x squared, so I'll do my shortcut. And so my, what do I have? 1/3 times the integral of u to the 4th du. So by reverse chain rule, I would have 1/3 u to the 5th over 5 plus, and we don't need the plus c, right? Because we're working on the definite integral. And u was at x cubed plus 1, so I have 1/15 x cubed plus 1 to the 5th. Okay, so now what I would do is I have to write that separately. And notice on this, I did not write any limits of integration here because when we've done this variable replacement with u, those limits don't matter or they don't make sense. So now I go back and I get 1/15 x cubed plus 1 to the 5th. And now by the fundamental theorem of calculus, we evaluate this from -1 to 0, which we end up getting 1/15 for our answer here. Now, the other way you could do this with u substitution, I think is trickier, but the other way is we are letting u be x cubed plus 1. So if we look at these original limits of integration, -1 and 0, in terms of u, so our first limit of integration is x equals -1. That would mean that u, in terms of this formula, would be -1 cubed plus 1, which is 0. And when x is 0, u would be 0 cubed plus 1, which is 1. So the other way, if we want to do u substitution inside this definite integral, when we make our substitution to u, what we would do is replace these limits of integration with our u values. So from 0 to 1 of 1/3 u to the 4th du. So if our variable inside our integral is u, and we want to write the limits, those have to be in terms of u as well. Okay, so we do not have any types of questions like this in our class. I just wanted to make you aware of this process in case you see it in your other classes. And you should in Calc 2, when you start up in Calc 2, I guess it's in 2 weeks, you'll do problems of this type, and you'll also learn integration by parts and some other methods of integration. So we've just barely touched the surface in our class, but that's the basic introduction. You should be able to apply it to your other physics, engineering, chemistry, whatever else. But I just wanted you to be aware that this process, what this sort of looks like. So are there any questions?